So, like I said at the start of this session, bit manipulation actually is going to be a lot more important when you're going into your microprocessors course next semester. And the information that you have in this particular lecture, it's handy to have later on in your microprocessors course next semester, because these tips and tricks you learn for how you can quickly manipulate your bits will actually prove to be quite useful when you actually do that particular course. You do get some of these questions on bit manipulation asked in your programming interviews as well, so it's handy to know how to answer these questions and how to manipulate your bits in binary form effectively as well. Now, in doing this, it comes like if we have to do some of these binary manipulations using some sort of technique to optimize your code. In reality, it's just basically to know how to use the bit manipulation operators in order to achieve these things. So even though that we need to learn it manually, we also need to learn how to do it automatically as well. So it's handy to know how to use both techniques. Because in an interview, you won't have these operators on hand. You need to actually know how to do the bit manipulations manually in order to achieve your objectives. So a lot of people think it's confusing to do this in binary, but in reality it isn't. It's just going to be a different numerical base. The rules at which how we do the addition, the subtractions, the multiplications and divisions remain the same once you're operating with any numerical base. Yeah, there's a good bit of rain here, so hopefully I can get this sorted out here. Hopefully you guys are hearing me somewhat. If not, hold on, let me see if I can alleviate this. Alright, you guys are hearing me any somewhat better? Hold on, let me see if I switch my microphone at the next. 1 second. No, that probably isn't working. Okay, 1 second, guys. Alright, so just bear with me. It seems to be like a passing cloud, hopefully, so it shouldn't be too long. So, a lot of people think using binary operations, it's going to be a little bit confusing because we're dealing with a particular numerical base. And the order of which we do these operations, it's going to be the same no matter what numerical base you're dealing with. So the same way we do addition, subtraction, multiplication, and division, it's the same way that how we go about doing these for any numerical base, even though we're doing binary operations. The confusing part tends to be how do the numbers wrap in the base, and how we do this manually in order to achieve our objectives. So initially I had a poll to go about doing these operations to see if you guys can figure it out. But in the interest of time, I'm not going to do that. I'm actually going to do these operations so you guys manually here on the slides. So you actually can see how we actually do these in a manual form for doing it. So we're going to be starting with this particular operation. So if this is 0, 1, 1, 0, and we have 0, 0, 1, 0 here, and we add into 2. So 0 and 0 here will give us a 0. 1 and 1 here, this comes like we did 1 plus 1, that will give us 1, 0. So we put a 0 here, and we have this 1 carrying across there. Now we have 1 plus 1 plus 0. That comes like the same thing if we have 1 and 0 here. So we put the 0 here, and we carry across this 1. And we have 1, 0, 0, which gives us 1. Now, just to do a quick verification here, 0, 1, 1, 0 in decimal, it's going to be 5. And 0, 0, 1, 0 here, it's going to be 2. So maybe I did my math wrong somewhere, because I ended up with a result of 8. So maybe I had to carry somewhere wrong. So actually, let's do this back step by step and see where did I make this particular mistake. And the reason why I'm making these mistakes is for you guys to actually see how do we make sure that we don't make these mistakes as a result. One second. Right. Okay, so let's say if I was doing the addition from left to right instead, so this would go 0, 1. Nope, same problem. Okay, I understand what I'm doing wrong. So end result here actually is supposed to be. Oh yeah, no, that is correct. Whoops, my bad. Yeah, that's 6. I thought it was 5. My bad. Yeah, let's say it was 6. So yeah, that was correct. Thank you for pointing that out. So our end result here would end up being 8. So let's just repeat this as well. So 0 and 0 is 0. 1, 1 will give us 0 because that's 1 plus 1. That's 1, 0. So we carry across this 1 here. We end up getting a 0 here as well. We carry across that 1. That's 1, 1, 1, 0, 0. Yep, thanks for that. Silly mistake of mine. I think I'm a little bit preoccupied with this rain interfering with my microphone. Alright, so for the second operation, which is this one here, we're going to use the bigger number on top, and we're putting the smaller number underneath for multiplication. So we can see here that 0, 1, 0, 1 is going to be the bigger number. So we have 0, 1, 0, 1. And then we have 0, 0, 1, 1 here. And we're going to be doing this multiplication as a result. So this comes like we are doing the standard long multiplication that we are accustomed to when we're using decimals. So we start with this particular number here first. So, should circle that. So we start with this particular number here first. And we're going to be multiplying the top number here by that particular number. So that comes like if we're just multiplying it by 1. So 1 and 1 here will give us 1. 0 and 1 will give us 0. 1 and 1 will give us 1. 0 and 1 will give us 0. And then when we move to this particular number, we put a 0 here, but it becomes like if we're going up one particular significant bit in our multiplication. And then we repeat the multiplication as is, which is going to be this top number here multiplied by 1. So we just put back the number here as a result. And then we just add the results here. So we get 1 and 0 here, which is 1, 0 and 1, which is 1, 1 and 0 here, which is 1, and 0 and 1 here, which is 1. And this 0 here, that's just basically 0. So in translating this back into decimal for verification, 0101 here is 5, and 0011 here is 3. So that means our end result here should be 15, which is 8, 4, 2, 1. Yep, that's 15, so that's correct. So the order of operations that we do here for doing these additions and subtractions and multiplications and divisions, it just follows the same standard rules for any numerical base. Once we follow these rules and we keep on doing these as required, it's possible for us to do any manipulation using any one of these techniques for any numerical base, be it binary, octal, hexadecimal, any other particular base 3, base 4. Once you do these rules here, you will always get the correct answer. And yes, it does happen that when you translate it back into decimal to verify, you may end up making a small mistake. But once you actually do perform the rules here correctly, you'll always get the correct answer no matter what. So I'm just going to clear the slide here for us to do the next two operations. The erase all link on the slide, right? Nice. So let's do this one here, which is 0, 1, 1, 0, and 0, 1, 1, 0. And let's just add the two together, so 0 and 0 will give us 1. 1 and 1 will be 1, 0. So if we put the 0 here, we carry across this 1. 1, 1, 1 will be 1 plus 1 plus 1, which is like 1, 0 plus 1, which will give us 1, 1. So we put the 1 here, and we carry across this 1. And 1, 0, 0 here will give us 1, 0. Alright, so that's 1, 1, 0, 0. And this here comes like if we're adding 6 here and 6 here. So this should actually give us 12. 8 and 4, yep, that's 12. So that's how we go doing this math in particular. The last one that we're going to be doing here is the subtraction, which is 0, 1, 1, 0 and 0, 0, 1, 1. So same standard rules when we're doing subtraction manually. 0 and 1 here, you can't actually subtract that, so we have to borrow a bit here. And we get 1 here as a result, so that's 1 minus 1, which gives us 0. 0 and 1 here, we can't do that as well, so we have to borrow a bit here. So that's 1 and 1 here, gives us 0. And we keep on doing this as such, and we see that in our subtraction here, we actually do some part of the operation here quite wrong. And in order to make sure that we're actually doing this operation correct, we actually need to actually go back to a little bit to our rules regarding this. So let's do a verification here in decimal first and see how actually we go out to the result. So 0, 1, 1, 0 here is going to be 6. And 0, 0, 1, 1 here is going to be 3. So we need to make sure that we end up with the result of 3 here as a result. So in formulating our result of 3 here, that means our end result needs to be 0, 0, 1, 1. So let's see what mistake that we made here as a result that gave us. So when we borrowed our bit here, which was 1, and we got 0 here, and we put this 1 here, this comes like here, this is 1, 0. So this is 1, 0 minus 0, 1. 1, 0 here is 2, 0, 1 is just 1. So this will just result in 1. So remember, when we borrow this bit, it comes like if we append that bit to our previous bit that we just had here. So this 1 here is not going to be 1 minus 1. This is actually going to be 1, 0 minus 1. So that's what you have to remember. So this is like if we put 0, 0 here and 0, 0 here. And this is 2. And this is 1. So 2 minus 1 will always give us a value of 1. Similarly, when we do this part here, which is 0 minus 1, we borrow a bit here. So that's 1, 0 minus 1 here. And we end up with a value of 1 here as well. And the remaining parts here, which are just zeros, will just be 0 and 0. So this is what you need to pay attention to, in particular, when you're dealing with subtraction operations, because it's quite easy to make this mistake. So these sort of things you actually need to be very careful about when you're dealing with subtractions, because when you borrow the bits, they append, they don't just substitute as a result. Alright, yeah, I know the rate is a little bit troublesome here, but are there any particular questions regarding any one of these operations? So we're going to see 2's complements in a little bit. So how it plays an important part. Alright, I'll just entertain that request. So let's see what that looks like. If we had 1000 minus 0011, so this comes like if we have 1, 2, 4, this would be 8, 3, so we need to end up with a result of 5. 5 here will be 0, 1, 0, 1. So let's actually verify how we do this. So 0 minus 1 here is 0, so that can happen. 0 minus 1 here is 0, that can happen. This can happen. So in order to go about doing this, this actually is going to be a little bit more tricky, because we can't have these borrows going on. So what happens in a case like this is that when we do our subtractions, if we go 0 here and we have 0 here, we can't borrow from zeros as a result. So when we do this here, it comes like if we strike this and we have 1, 0 here, and if we strike this here, but when we strike this here, 1, 0 minus 0, 1, this comes like with 2 minus 1 here, so that's just going to be 1. So this entire thing here just becomes 1. Similarly, when you have this 1, 0 here and we strike this, this entire thing here just becomes 1. And this 1, 0 here will just be the same thing as before when we do our borrows. So this 1, 0 here minus 1 is the same thing as here, which we did. So this will result in 1. 1 minus 1 is 0. 1 minus 0 is 1. And 0 is 0. So remember, it's just to pay attention to how you draw about the append bits as a result. Because when we did those particular operations, and we borrowed in particular, the append bit, when we did the initial borrow, it ends up in 1, 0. So when we did that borrow here, we had 1, 0, which is 0, 0, 1, 0. And then if we borrow again, this comes like we minus 1 from this. There's a 0, 0, 0, 1. And it's like 2 minus 1, so it means we have to get 1 here, so the result here is just to be 0, 0, 0, 1. So that's how we end up striking this entire thing here, and we got 1 in particular. And we kept on doing this until we were able to complete the subtraction as a result. Alright, so hopefully that answers that particular question. It's just basically using the same rules from your subtraction and decimal. Once you understand how the rules operate, you're pretty much okay. Any further questions? Alright, doesn't seem like we have any further questions, so let's move on for the time being. So, there are ways for us to speed up our operations, so let's watch back this one in particular. Well, we had the same number here being added twice. This actually is if we did 0110 multiplied by 2, because it's the same number. Now, a multiplication by 2 in binary is basically equivalent to shifting the binary number left by 1. So when we shift this by 1 to the left, that's 0110, and we shift that to the left, we drop this 0 here, we have 110, and because it's a 4-bit number, we add a 0 onto the end here on the right. So we got 1100. So that's a very quick way to do a multiplication by 2 in binary. If we shift it to the left again once, it comes like if we multiply by 4. Because this is like the same number here multiplied by 2, and then we multiply the result by 2. And we keep on going, it's just like if we keep on doing successive multiplications by 2 for the entire number. So that's a nice quick way for doing multiplication by 2 in the binary formats that we're dealing with here. There are other operations to consider, and some of them you already know, which is basically your AND, OR, XOR, and NOT gates, which you have seen so far in digital electronics and some previous courses. But the two operators that you need to know about here is going to be logical shift left and logical shift right. And I have mixed up the symbols here. They're supposed to be the other way. So let's correct this. So logical shift left is supposed to be brackets to the left. Logical shift right is supposed to be brackets to the right. So for instance, if we put this operator here in our C++ code for binary number 0011, we shift this number to the left by 2 digits as recurrently. So when we do this, this comes like we do basically 0011 multiplied by 2 multiplied by 2. And when we do this shift, we'll end up getting this being equal to 0100 multiplied by 2 equals to 0110 1100. If we logical shift to the right, it's basically the converse, like if we divided by 2 instead. So where we had, in a particular case, let's say we had 0110, and we wanted to divide this entire thing by 2, and we did a logical shift to the right, this will end up being 0, 0, 1, 1. So this is like if we say 6 here, divided by 2 gives us 3, and this result here is 3. So logical shifts to the left multiply by 2, and a logical shift to the right divides by 2. Now, this particular slide is very useful for bit manipulation. And these 9 operations that you see here in the bullet points are very handy for doing any sort of operations. So it's very important to remember these in particular. So like, for instance, if we have x and some x here where x is our bit pattern, or some input binary number, and we XOR that with zeros, we'll get back the same number. If we XOR that same thing with a sequence of ones, we'll get not the value of x. And if we XOR x with itself, we will get 0. So to answer that question, if we had 0, 0, 1, 1, and we shifted it to 4. So yes, it will spill over because in this particular case we're dealing with a 4-bit number. But like, let's say if we were dealing with an 8-bit number, so if this was 0, 0, 0, 0, 0, 0, 1, 1, and we shifted that by 4, this comes like this goes 1, 2, 3, 4. This will end up being 0, 0, 1, 1, 0, 0, 0, 0. But if we were dealing with a 4-bit number, yes, it will spill over and we won't get the results. The end result here for a 4-bit number will just end up being 0. We won't get the result because there's not enough bits to represent it. But if we had 8 bits, it's possible for us to actually represent this number. So you need to be a little bit careful with the bits being spilled over as a result. So that's a nice thing to point out there. Right, so going back to our bit manipulations, the XOR gate is actually a nice way for us to do manipulations on your X, where X here is any input binary number. So if we had X here XORed with a sequence of zeros, we'll get X being our original value. If we XORed it with a sequence of ones, we'll get not the value of X. If we XOR it with itself, we'll get 0. And if you're asking why, think about how the XOR gate operates. It only gives a value of 1 when they are opposite bits as a result. With the AND gate operations, if we AND our X bit pattern here with zeros, we'll get 0. If we AND it with ones, we'll get back X. And if we AND it with itself, we will also get back X as a result. Because the only way you get a 1 with your AND gate is if you have ones on the inputs. But the OR gate here, if we have X and we OR it with zeros, we'll get X. If we have X and we OR it with ones, we'll get only ones. And if we OR X with itself, we will get back X accordingly. And this is because of the operation of the OR gate. An OR gate operates such that once there is a 0 on the once there is any 1 on the input, the output will be 1. So these 9 particular operations here are important to know for doing quick bit manipulations. As a result, using your logic gates, which can actually be implemented in programming as well. Any particular questions regarding these 9-bit operations? Feel free to ask now. So XOR is basically once you have conflicting bits on the inputs. Like we have a 0 and 1, or a 1 and a 0, you will always get 1. If the input bits are the same, meaning 0, 0 and 1, 1, you will always get 0 for your XOR gate. So when you XOR basically with zeros here, you will end up getting it such that you only get 0, you'll get back your X as a result. And if you XOR with ones, you will basically come like you invert your X as a result. The pipe operator is the OR gate. So an OR gate is basically once you have a 1 on the input, you will always get a 1 on the output. So each one of these gates operators here, you actually can try in your C++ programming language to actually see how it operates. And you can see how it goes about doing this. No, X actually represents your input binary number. Right? Any other particular questions? Alright, doesn't seem we got any particular questions. Alright, let's go on with our lecture so far. Right. So your computer basically stores integers or any particular number in something referred to as two complements representation. So a positive number is basically represented as itself, but however the negative number is going to be the two complements of its absolute value. And the most significant bit being this one bit here is going to be your sign bit that's going to be indicating that this is a negative value. So let's watch this for a 4-bit integer here, which is 3 in decimal. So we're going to have 1 bit for the sign and 3 bits for the value if you're doing 2 complements. So we need to watch this complement with respect to 2 cube here, which is going to be 8, right? So the complement of 3, which is going to be negative 3 here, with respect to 8 in decimal, will end up being 5. And let's actually watch this, how we formulated this, right? So in binary, this will be 1, 0, 1, and as a result for a 4-bit number, we'll get 1, 1, 0, 1. So let's see the steps on how we did this. So the positive version of this for a 4-bit number would be 0011. For a negative number, we need to watch this such that, okay, the most significant bit here represents a sign, so 0 is positive, and 1 here is negative. So we have a 1 here. That 1 here represents -8. And then the remainder here needs to add to this in order for us to get back this value of -3. So to get from -8 to -3, we need to make sure that we add a value of 5 here in order to get this. And 5 in binary is 101. So that's how we get 101 here as a result. This is like a very quick way for us to actually go about doing this for 2's complement. The other way to do this is basically you invert the bits in the positive representation and you just add 1 and you prepend the sign bit. So instead of watching all the 4 bits here, we start that we have 0, 1, 1. We flip the bits. So we get, instead of 0, 1, 1 here, 1, 0, 0. And then if we add 0, 0, 1 here, we get 1, 0, 1. And then we need to put the sign bit here. And then we put this remainder here. And that gives us our 2's complement representation. So that's the other way to go about doing 2's complement, doing it step by step as a result. Either method is fine. Once you understand how it operates, whichever one you're more comfortable with, that's fine for 2's complement. So one thing to note between unsigned and signed bit numbers is that the range of how many numbers can be represented is going to change. So if we had an unsigned for a 4-bit number, this will go from 0 to 15. But with a signed number, it ends up going from -7 to +7. So these difference in ranges here in between unsigned and signed bit numbers is something you actually have to pay quite attention to when you're dealing with either one of these. So it comes like if we just end up shifting the range numerically, because instead of going from 0, 1, all the way to 15, now we have -7 to 0 to 7. So that's what you need to pay attention to in particular. So it comes like if we have first half and then a second half. So the first half here will be 0 to 7, the second half here will be 8 to 15. The second half here is what ends up getting flipped here as a result from moving from signed to unsigned. Sorry, from moving from unsigned to signed. So that's what you need to pay attention to in particular when you're dealing with these. Now, there are 2 types of right shift operators you need to pay attention to when you're dealing with these particular operators. So, there's a key difference between arithmetic right and logical right. Arithmetic right will do your divisions that we have seen so far. However, logical right just shifts the bits. It will not do that division for you. And we're going to observe this with a negative number as what's going to be the key difference between the 2 of them. So a logical shift right will shift all these bits here to the right by 1. So it will put this one here, this one here, and this one here, and so forth. But however, it will put the most significant bit here as 0. And this is indicated with a triple operator instead of a double operator for a logical shift right. And note the difference in results here, where we had negative 75 here for our signed bits. As a result, when we do a logical shift right and we have 0 as the most significant bit, we end up getting a result of positive 90, which is not the same thing as your arithmetic shift. So this is something you need to pay attention to. Logical right shift and arithmetic right shifts are different. Logical right shifts just shift the bits and it does not take into consideration what the sign bit is. Arithmetic right shift will take consideration of what the sign bit is and return the right value for you. So the arithmetic right shift will actually shift these values here accordingly, but it will fill in this new bit here with the value of the previous sign bit in order to maintain its composure. And this is just going to be a double symbol operator for your arithmetic right shift. And yes, it divides the number by 2 roughly, because we can't really represent a decimal number in this form. So that's what we have to pay attention to when we're dealing with it. The same also holds true for arithmetic left shift and arithmetic and logical left shift. One maintains the sign value, one does not maintain the sign value. But it's more evident when you're dealing with right shifts because of that sign bit you're going to be dealing with here as a result. Now, getting and setting in your binary numbers, it's important to know how we do this. And it's somewhat important to understand how they actually do operate and try not to memorize them because you may actually get asked to do these manually to form your results. So I'm going to give you guys some example code here on the next few slides as to how you can actually achieve some of these operations. So if we need to retrieve a particular bit in every binary sequence of bits, this comes like if you're trying to do a bit extraction at a particular position in your binary number. So if we wanted to extract 1, 2, 3, 4, 5, the 5th bit here in our 8-bit number, we create a bit mask here where only the 5th bit is 1. And all the other bits here are 0. And then we add this with our input variable here, which is num, input binary value. So as a result, it clears all the other bits, and we retrieve this particular bit at the 5th bit. And we compare the result with 0. So if the result does not give us a value of 0, that means we excessively subtracted a positive bit here. But if it does return a value of 0, that means in the original bit sequence, bit 5 there was originally 0. So the general code for this is given here for your get bits. To set your bit, you use the same bit mask as before, but instead of using instead of using an AND operation, you end up using an OR operation instead to do this. So your end result will be that all other bits in your result will be 0, and it will not affect num as required. And the example code for this is given here as well. If we wish to clear a particular bit in our binary sequence, we create a bit mask where all bits are 1 except for the bit we wish to clear, which is going to be 0. And to create this, we do the same thing as if we were doing it for our previous operations. So we had where we were setting the bit or getting the bit as required. And we just invert this to get the bit response for bit mask. So once we have this inverted bit mask here, and we AND it with our input variable num, this will clear that bit here at that particular position and leave all the other bits unchanged. This is the general code for this as well. If we wish to clear a set of bits, we need just basically to do the same thing as before, where we just put zeros for the bits we wish to clear. And then we just go about ANDing it as a result. The quick way to do this is that if it's going to be a sequence of bits that are sequential in nature, we go up one bit further and we put 1 there at that particular bit, and when we subtract 1, you'll get a sequence of zeros followed by the sequence of 1s as required. Alright, so let's see what you're talking about for the get bit. So I'm just going to illustrate this here. So let's say if we had some input value here, 0, 0, 0, 0, 1, 0, 0, 0, and we wish to check to get this particular bit here. So we have 0, 0, 0, 1, 0, 0, 0, 0. That's the bit we want to extract. If we AND this, 0, 0, 0, 1 and 0 and 0, 0 and 1 is 0, 0, 0, 0. So if this entire result is 0, this means that this original bit here was 0. So that means once we get this and we get the result here being all zeros, this original bit here that we were checking for is going to be 0. Conversely, if we had a value of 1 here, and we AND this, 0, 0, 0, 1 and 0 will give us 0, 1 and 1 will give us 1, 0, 0, 0. And when we compare this again with 0, that means that this bit here, this bit here, was actually a 1. So that's how we actually do the illustration for this, to actually do the checks and whatnot. So that's how you make sure when you retrieve those bits, or you retrieve a particular bit, that's how if you know a bit at that particular position was set as 1 if it was cleared as 0. Alright, let's go back to this clear bits here. So if you're clearing the bits here from most significant to I bits, in creating the bit mask, it's a lot easier to do this by setting that 1 at the I bit and just subtract 1 from that bit mask. So you get a sequence of zeros followed by a sequence of 1s. And then you just AND it with your input numerical value, and it will leave the lower part of num change, and the upper part is not going to be changed. So to give an example of this, let's just put a random value here. So let's say 0, 1, 0, 1, 1, 1, 0, 0. And let's say we want to declare the first 4 bits here. Actually, no. Let's leave it as that. So when we make our bit mask, it comes like if we make 1, 0, 0, 0, 0, 0, 0, 0, And the ith bit here is this point here. So nope, I did that wrong. So we make the I bit here, when we watch, we start creating our bit mask here up to the I bits. So we put that 1 here as a result. When we minus 1 here, this will go 0, 0, 0, 0, and all these bits here become 1, 1, 1, 1. So if we AND this sequence here with our original input sequence, one and 0 here will give us 0, 1 and 0 here will give us 0, 1 and 1 will give us 1, 1 and 1 here will give us 1, and all these zeros here will give us 0, 0, 0, 0. So this part of the number here is the same as this part of the number here. And all these parts here will clear from our original number. So that's how you go about clearing bits from the most significant bit up to a set bit as a result. So the code for this in C++ is given here as well. I would say most of these methods are very simple little lines of code. It's just a matter of knowing how to go about doing it. To clear one particular bit was this particular method here. So I'll just do an illustration here for you guys as well. So let's say if we had 0, 1, 1, 1, 0, 1, 0, 1, and if we wish to clear this bit here, it comes like if we made a bit mask such that everything here would be 1, 1, 0, 1, 1, 1, 1, 1. And if we AND this, 1 and 1 is 1, 1 and 0 is 0, 1, 0, 1 and 1 here is 1, 1 and 0 here is 0, 1 and 1 here is 1, 0. So this particular bit here is cleared as a result, and all the other bits here in our original number are maintained. So it's just basically a sequence of set of tricks that you just basically need to know to go about doing these clear bits and set bits and how to retrieve particular bits and whatnot. It's just basically some simple sequences that you just need to know. So if we need to clear from the ith bit to the least significant, we basically take a sequence of all ones. No, the bit mask isn't random. You're cherry picking to make sure it's certain bits. That's how you go about doing these clears and whatnot. So you actually do have to cherry pick. So if you're clearing from the ith bit to the least significant, you take that, you start with a sequence of all ones, and you shift it left by I plus 1 bits. And this basically gives you the sequence of ones followed by the 0 bits as required. And then you AND this accordingly with your numerical input value. So let's say, for this particular case, if we had 1, 1, 0, 0, 1, 1, 1, 0, and we wish to clear these 5 bits here, when we start our sequence of ones here, it's going to be 1, 1, 1, 1, 1, 1, 1. Up to here is your ith bits. So we need to make sure that we shift this entire sequence here by I plus 1. So when we do this shift here, we'll get 1, 1, 1, 0, 0, 0, 0, 0. So we have our input here. And we're going to be using this here to do our clear, which is 1, 1, 1, 0, 0, 0, 0, 0. And if we AND this, 0, 0, 0, 0, 0, 0, 0, 0, 1 and 1 here is 1, 1 and 1. So we can see here that these 5 bits here, from the ith bit down to the lowest significant bit, have been cleared, and this part here remains the same. So yes, you can cherry pick, but the methods that I'm giving you here on the slides actually help you speed up the process using these particular tricks. So this is the code here for basically clearing from the ith bit to the least significant. Alright. So that basically brings us to the end of our bit manipulation lecture. And what we basically observed is that we saw how to do operations in binary, how to pay attention to particular rules that we saw for any other particular numerical base. When we came to addition, subtraction, multiplication, and division. And we also saw that how to clear bits and get bits and set bits and whatnot. It's important figures for us to know how we go about manipulating the bit masks and to use the AND operations to go about doing this. So in coming up with the bit mask, to answer your question here, so and when we forget, okay, so we select which bits in particular we're going to extract, and we just, for bit mask, we only put a 1 for that particular bit. For sets here, it's the same method, but instead of using the AND operation, we use the OR operation. So for that particular bit in the bit mask, we put 1, but all the other bits are going to be 0. To clear, the bit that we wish to clear must be 0 in the bit mask, and all other bits must be 1. If we wish to clear a sequence of bits, so let's say from the most significant bit down to some ith bits, these bits here must be 0, but all the other bits must be 1. So in order to do this automatically, we make sure that we have a bit mask here with 1 at the ith bits. And if we subtract 1 from this, we get the bit mask that is required. Because all here will just become zeros, and all these bits here will become 1 as a result. So this is a very quick way to set the bit mask. If we are clearing from the ith bits to the least significant, we start with a full bit sequence here of all 1s, and then we just shift all those bits to the left up to I plus 1. So if this is ith here, this position here will be I plus 1. And when we do that shift, all bits up to I plus 1 will become 0, and all the remaining bits will become 1. So that's how you come up with these bit masks for each one. So it's just a matter of knowing which bits you wish to get, which bits you wish to set, and which bits you wish to clear. For setting in particular, if we backtrack, setting is where you basically set which bits you want to extract. Sorry, for which bits you want to set as 1. You make sure in the bit mask at those positions, those bits here are 1. If you are clearing, you want to make sure that those bits in the positions required are going to be 0. For the set operation, remember this is going to be an OR. For your gets and your clears, it's going to be AND operations with the bit mask. All right. Any other particular questions? So for microprocessors, you are going to need a good understanding of electronics. It doesn't necessarily only need to be op amps. You actually have to know about interfacing circuitry. So what are the required voltage levels, what are the required sink and source currents, and so forth. You need to also make sure that you know a little bit about digital electronics to know which voltage levels you're going to be operating in. And in particular, what you need to pay attention to is how does your safety circuitry also operate with the microprocessor in question. When you're finished wiring your microprocessor, because this is a hardware aspect, and you tested it to make sure that it's running as intended, then you only, and then and only then can you program your microprocessor. So the hardware aspect is going to be electronics based. And once everything is wired up properly and you power on and your processor is running fine, only then can you program it. The programming aspect, in particular, what you're going to be using most of all is going to be this particular lecture, the bit manipulation lecture. Because there are a lot of things that you will end up doing in binary regarding these processors, because there are very small bit processors. So it'll be like an 8-bit processor or a 16-bit processor. And you're going to be doing a lot of bit operations to get certain operations done and in order to interface with your hardware and so forth. Things that you actually need to go about preparing for micro-P, it will be this particular lecture for the software aspect, as well as for the hardware aspect. You want to make sure that you're able to wire things like to do proper circuitry for LEDs, so proper safety circuitry. You want to learn about pull-up and pull-down resistors. You also want to make sure that you know about grounding things properly, how to avoid faults. And you also want to make sure about how do you interface different types of circuitry by paying attention to their voltage levels and how you can go about doing current limiting and voltage limiting in particular. It's going to be very rare that you may end up using an op amp in micro-P. If you do end up using it, most of the times it ends up being something similar to that of a comparator or some sort of rectifier. But it's very rare you're going to end up using an op amp. Alright, nice. Any other further questions? Okay, it doesn't seem like we got any further questions, so I do apologize for the rain situation here, because I knew my audio wasn't at its full capacity and clarity, but I couldn't help. I couldn't really help that. It's just the weather. Quiz 3 would be in 2 weeks' time on the Wednesday, if I am not mistaken. One of your class reps may correct me if I'm wrong, but I'll check back what they negotiated for you guys as well to make sure if it's going to be on the Wednesday, if it's going to be on the Saturday in 2 weeks' time. And once I check it back, I will make sure to post up a forum post in advance so that you guys will know as well. But in the meantime, if you do need to have a good estimate before I actually do all these checks, you can actually contact your class reps and you can ask them what's going to be the new dates, because they did some negotiation with Dr. Kuransing to accommodate for your midterms and whatnot that are coming up pretty soon. Quiz 3, what I can tell you is going to be highly focused on, let's see what topics I had here. So I'm just going to check this back for you guys. So what I can tell you for now is that quiz 3 is going to be highly focused on trees and graphs. And there is a very high probability, it's not for certain as yet, that quiz 3 will have no multiple choice questions. It will just end up being long answer questions. That's all I can tell you for now regarding quiz 3. Alright, so if there are no further questions, feel free to leave any questions down in the comments below or directly email me. I'm available on email or the forums. If you ask any particular questions, I do tend to respond pretty fast unless I'm out of contact. But you will get a response basically within 24 hours, if not probably the next working day, if in worst case. If you do require any tutorial sessions from here on out, feel free to request them in advance. And let me know what particular topics that you need to do in advance as well, so I can actually prepare for these, and we can have very direct tutorial sessions, get it straight to the heart of the problems and resolve these problems very effectively. Right, I'm getting to that. This actually is our last programming session, teaching session for all these lectures. So no, we will not be having any class on Wednesday. Like I said, if there are any further tutorial sessions that are required, feel free to request them in advance along with the particular problems that are being encountered, so you can get direct and straight to the point with these. Alright, so good luck with the rest of the course, and make sure that I hope you guys do well, because most of the material that we did cover here in these lectures are good sufficient material to prep you guys for any internships that you are going to be applying for in the near coming future. And good luck in getting through with those internships. Once you know the materials for these, for the programming aspect, you're pretty much set from studying these lectures and practicing the particular questions that you did encounter in your quizzes and so forth, and in particular your group assignments. Those sort of questions are the same sort of questions that you're going to encounter on in your internship interviews regarding your technical knowledge when it comes to these sort of things. Alright, so until possibly a next requested tutorial session, or probably sometime any other time, take care, be safe, and I will see you guys soon. Later.